Welcome back, everybody. This is Meyer, and in this video what we're going to be doing is talking about sound. In fact, this entire week what we're going to be doing is talking about the science of sound, how sound works, what are the important properties of sound, and then talk a little bit about the frequency domain. And understanding how sound works and how it's represented in the frequency domain is super important for producers, and I think this is one of the big stumbling blocks that trips up new producers, is understanding how sound is represented in the frequency domain and how that's different from the time domain, which is the way we usually think about sound. So once again, you may not know any of these words that I'm talking about. Don't worry, we're going to get into it. So the first thing I want to do is talk about sound being a wave, because when we talk about waves, and by waves I don't necessarily mean ocean waves, I mean waves in the physics sense of the word. So if you remember way back to high school physics, what are waves? Well, that's what we're going to be talking about, because waves are an important way that we can use to describe sound, both in terms of sound as a physical description of what sound is and as a displacement of air, or how it's represented within a computer, which is completely different. So if you remember back, waves are just a transfer of energy, and there are two types of waves. There's longitudinal waves, where the energy is transferred through the wave, and then transverse waves, where energy is transmitted across the wave. So it's like, you kind of have to think about the differences between these two, and we don't have to get too technical about this, but when we talk about sound being a wave, basically it just means that sound is a transfer of energy through a medium of air. So waves are periodic, and this is why we're going to spend time talking about waves, meaning that they repeat every so often. And the important thing about the fact that they're periodic means we can actually measure the period of the wave, which is the time it takes for a wave to complete a single cycle. So basically what you do, you start the timer when the wave starts at some point, and there's no real starting point because the wave is just kind of going on and on and on. So you define some arbitrary starting point, start your timer, and then when the wave reaches that point again, it's completed an entire cycle, you stop the timer, that's what the period is, meaning it's the time it takes that wave to complete one cycle. Whereas frequency is the inverse of period, which is the time it takes to complete a cycle. So if you think of period being the time it takes to complete one cycle, frequency is the number of cycles the wave is repeating in a given unit of time. And if the period is really large, or it's longer than your unit of time, you may end up with something like 0.2, meaning it completes 0.2 cycles every unit of time. And usually when we're talking about sound, we're talking the period is going to be, or our time unit is going to be seconds. So the period of a sound wave, usually it's like the seconds or the amount of time it takes to complete a cycle, whereas frequency is the number of cycles per unit of time. Now, this is also related to this idea of wavelength, which is actually the measurement of distance that the wave travels. But when you're converting between period, frequency, and distance, you need to actually know the speed at which the wave is traveling. So with sound, you have to factor in the speed of sound coming into play in order to calculate the wavelength of each different frequency. Whereas with something like light, you're actually dealing with the speed of light. So a couple things that waves tend to have that we want to talk about. We have, of course, a phase shift, which is just the offset between two waves. Now, phase isn't really a property of a wave itself. It's only really defined relative to some starting point that we define. So it doesn't really make sense to say, oh, like this wave is at 180 degrees, because when we think about it, the wave has just been kind of going on and on. Theoretically, we are just basically saying we're going to define the start point here, and then when we talk about this thing being out of phase or ahead or behind or something, that's just relative to wherever we started our starting point or wherever we started our stopwatch. When we think about waves, and you look at this picture here on the right, there are a couple of these properties of waves that also apply to sound. You have your amplitude, which is basically how strong the wave is or how much displacement it's caused. You have your crests and troughs. So generally what happens with the waves is we define this like 0 point that it's oscillating around, and then the wave goes up above the 0 point, or what we're going to call the zero crossing. It'll then hit the middle again, it'll go back down, and then it'll come back and complete a single cycle. So notice how this complete cycle isn't when the wave necessarily returns to its zero crossing. It's when it's completed its entire, pattern, and it repeats that pattern again. Waves obey this property called superposition, which basically means when you add two waves together, you're going to get a new wave, which is basically the sum of the other two waves. However, based on the phase, frequency, and amplitudes of the waves that you're adding, you can get different results when you're adding them together. So two waves added together in phase results, if they're the same wave, in just basically a louder version of that same wave. Two waves 180 degrees out of phase with each other are actually going to cancel out, or phase cancel. So that's a wave plus its phase inverted version. you're going to get nothing because they're going to cancel out at each point. And if you add two waves together at different frequencies, you're going to get an entirely new wave that may have a different period or a different frequency that it repeats at. So this is really important when we start talking about things like balanced cables, which is basically a way that you can transmit a signal across a long distance and basically cancel out the interference. So what ends up happening at the starting point of this cable, you send because this has three conductors in it, or like an XLR cable has three conductors, has your ground, it has your positive terminal and your negative terminal. So what you do is you send out your ground or your reference voltage, then you send out a positive version of the signal, and you also phase invert the signal and send out a negative polarity version of the signal on the other terminal. As this goes across the length of the cable, there might be some noise or interference or crosstalk that gets added, but generally what happens is it's going to get added to all three of those conductors together about equally. So when it reaches the end, what ends up happening is it takes the negative polarity signal, which has been phase inverted, and phase inverts it again. Then what ends up happening is the two signals are added together, the positive and the negative version. So what you end up getting is those two add together and you get a louder version or a stronger version of your original signal. And any of the noise that got added along the cable is now phase inverted when it's added to the noise of the positive terminal, and that noise tends to get phase canceled out. And that's why when you see in any live performance or DJs or things like that, they're generally going to be using balanced cables because it eliminates a lot of that interference that you would get. Sometimes that's a hum or a buzz or something like that, anything that could potentially interfere with your signal, and it pretty much cancels a lot of that out. So that's a cool way you can see phase kind of put to use here in an actual setting. Now, the reason we're talking so much about waves, of course, is that sound indeed is a wave. And sound has a couple different properties that are related to the properties of waves. But the important thing to realize is when we're looking at a waveform like this picture here on the right, what we're actually doing is describing what the speaker cone is doing. So when the speaker cone is resting, what's going on is there's no voltage applied to this speaker cone. Whereas when we apply a positive voltage to the speaker cone, usually it's a positive voltage, what ends up happening is it creates a magnetic field which pushes the magnet or pushes the actual speaker cone forward and outside of its resting place. And what this does is this creates areas of compression in air, which compresses the air molecules together. Then what ends up happening is the speaker cone is going to return to its resting place, and then as we apply negative voltage, it's going to actually pull back from its resting place and go to this area of where we call rarefaction, where it's actually pulling the air molecules apart. So this is a graph whenever you see a waveform like this of what you're physically telling the speaker cone to do. You're saying go forward, push in this amount, go back to resting place, and then pull back a little bit. And what's going on to the air molecules is as it's compressing them, it's pushing them tighter together and it's pulling them back. And that pushing and pulling of air molecules is what your eardrum picks up and what your brain interprets as sound. So based on how quickly this is happening or how strong this is happening, so how much displacement this is by the speaker, is going to be picked up as your brain as how loud the sound is. Of course, how fast is going to be the frequency, things like that. When we look here inside a digital audio workstation, so this is here within Studio One, and we look at an audio file, we can actually see this dynamic playing out. So here you have time on the horizontal axis and amplitude here on the vertical axis, or how much displacement or how strong these waves are. And what's actually going on here is this is actually measuring, as this playhead goes from left to right, what it's asking your speaker cone to do. Now the reason we have two waveforms here, of course, is because this is a stereo signal. You have your left and your right channel. So whereas the top is probably going to be your left, the bottom is going to be your right, and that's why you have your two waveforms in an audio file. Now not all waveforms are in stereo. You have some that are just in mono, which means it would just be one waveform that's then transmitted both to the left and the right channel. But that's kind of why you see these two pictures. You have one for your left speaker and one for your right speaker, and each one is doing that. It's describing the displacement that each of those speakers is going to undergo. Thanks for watching. If you guys have any questions about waves or anything, feel free to leave a comment or join the Discord where we can talk more about this. Other than that, thanks for watching, and I'll see you guys in the next video.